Okay, this is going to be the video for section 2.2 for differential equations and separable variables. And so far what we've been talking is, we've been talking about what differential equations are, defining terms of how to classify them. We've been talking about how to determine if something is a solution to a differential equation, or maybe where the interval where solutions would be unique, things like that. But we haven't actually learned any methods yet for finding the solution to a differential equation, and yet that's mostly what this class is. So this is going to be the first section where we start learning methods of differential equations. And basically what's going to happen here is this is going to be kind of like a series of recipes. We're going to say if an equation is of a certain form, then people have figured out that this particular procedure will produce a solution. And that's mainly what we're going to look at is different methods that work for different forms of differential equations, right? In chapter 2, we're restricting ourselves to looking only at first order differential equations, which means the highest order derivative is a first derivative, okay? All right, so the first method we're going to talk about is separable variables. This is a really nice technique. It doesn't work all the time, but when it does, it's very powerful. And so a separable differential equation is one where you can separate the dependent and independent variables on separate sides of the equal sign, okay? Then if you can do that, then you can solve by just taking the integral of both sides, okay? So for a different first order differential equation, if you were to write the derivative on the left side and then the function of everything else on the right side, then you would find that if you can factor that function on the right side into two parts, one that's a function only of x and one that's a function only of y, then it's possible to write the equation as something where the y's are on one side and the x's are on the other. So if I have this written in terms of dy dx, where y is the dependent variable and x is the independent variable, then I'm going to make the left side the y and the right side the x. Okay, here's how that would work. Here's an example of a separable differential equation right here. Let me use this, right? This side is separable. And that's because this right-hand side can be factored into the y part separate from the x part. It may not look like that because we have a mixture of x and y here, but actually e to the 3x plus 4y can be rewritten e to the 3x times e to the 4y, because when you have like bases, you add exponents. And then that means that you can take the x part and separate it from the y part, okay? Whereas this one over here, there's no way to factor this expression so that you have some function times some other function where there's only x's here and only y's here. So this one's separable and this one's not separable. Okay, so this method we're going to talk about here will only work for the equations that follow this kind of a pattern. All right. All right, so let's take an example one. What we would do if we are able to separate that, where we could separate this into the right-hand side is a g function that's a function of x times an h function that's a function of y, is we just do this. We just take this and divide both sides by the h and multiply both sides by the x, so that we get 1 over h times dy equals g of x times dx. And that means that by multiplying the dx to this side, only the x's are over here, and then we divide out the part that's y over here. We've separated this into a y half and an x half. Okay, if we're able to do that, then all we do to actually, the process is just to take the integral of both sides. Okay, so let's take an example. Let's say we have the differential equation dy dx equals x times y. Okay, this is separable because we can multiply both sides by dx and divide both sides by y to get 1 over y dy equals x times dx. When we take the integral of both sides, the integral of 1 over y is the natural log of the absolute value of y plus an integration constant, which I'm going to call c1. And then the integral on this side, x is the variable, this would be 1/2 x squared plus an integration constant c2. And so typically what we do is we just move this integration constant over here and make a new integration constant that's the combined total and just call it c. So this would be natural log of absolute value of y equals 1/2 x squared plus some constant. And this is producing an entire family of solutions with different integration constants. If we happen to have also an initial condition, then we can plug in that x and y and solve for the c for that particular solution. Okay, this is a solution, but it's called an an implicit solution because we have not yet solved for y as a function of x. It's a relationship that shows the connection between x and y, but it's not yet solved for y. Some solutions you can further solve and find an explicit solution. Some you can't. Okay, let's go ahead. In fact, actually, let's take that one and see what we would need to do to solve this explicitly. If we wanted to produce this explicit solution, then you would have to undo the natural log by doing e to the x on both sides. They would cancel on this side and leave the absolute value of y equals e to the 1/2 x squared plus c. But that's the same as e to the 1/2 x squared times e to the c, which is just another constant. So the form of this is y equals some constant times e to the 1/2 x squared. Okay, so this constant here, you could establish for some particular value, right? It may or may not be important in a particular problem as to whether or not you need to deal with the absolute value. So this is a solution, and this is what we call an explicit solution because it's solved for its dependent variable. Okay, let's look at another example. If we have this differential equation, dy dx equals y squared minus 4, you could multiply both sides by dx, divide both sides by y squared minus 4, and get this, and we've succeeded in separating the variables. Okay, now if we were to try to take the integral at this point, right, there's no real easy way to do this integral here, right? It doesn't fall apart when you make a u substitution for the denominator. It doesn't really match well, I guess it would match a form in a table. We could use a table to find this. But another technique for finding complicated integrals, if they're in the form of a ratio, a fraction, is you can use partial fraction expansion. So this is a topic that's taught, I believe, in Calc 1. If you have something in the form 1 over y squared minus 4, and that denominator can be factored, for example, into this case, into y minus 2 times y plus 2, then that means this expression can be written as a sum of partial fractions, each with a constant over a term. So you can have a constant a, which I currently don't know, over y minus 2, plus some constant b over y plus 2. And it's tedious, but not too hard to figure out what these constants are. What you have to do is get a common denominator throughout. So this term here would have to be multiplied by y plus 2 over y plus 2. And this term here would be multiplied by y minus 2 times y minus 2 so that everything is the same denominator. And then the numerators are that a times y plus a times 2 plus b times y plus b times negative 2 has to equal 1. So you end up in an equation here. And then what you can do is you can group all the terms that have y and all the terms that don't have a y. And then you'd say, okay, so a plus b times y plus 2a minus 2b has to equal 1, which is the same as saying 0 times y plus 1. And then you make these things match. So the y term here, a plus b, has to equal 0, and 2a minus 2b has to equal 1. And that forms a little system that you can solve to figure out what the constants are. So that means that since a turns out to be 1/4 and b is negative 1/4, right, you could say, okay, 1 over y squared minus 4 can be rewritten as 1/4 over y minus 2 plus negative 1/4 over y plus 2. And if you replace that in this left-hand side, that means that this left integral becomes two separate integrals. So in other words, the integral over here of 1 over y squared minus 4 dy, we've got integral of 1 dx over here, right? This is the differential equation. We're going to take this left-hand side and separate it into two separate integrals, each one with one of the partial fraction expansions. And these are easier because you can use a u sub to say, let me just take this one right here and show you this on the side. This is fairly straightforward, but just to make sure. So the 1/4 can come outside. And then you'd have the integral of 1 over y minus 2 dy. So typically what's going to happen is you would do a u sub. So therefore u dy would be 1. So du is equal to dy. And then when you substitute here, you would get that this is 1 over u du. So this ends up being 1/4 times the natural log of the absolute value of u, which is 1/4 times the natural log of the absolute value of y minus 2. So as long as there's not a power here, this antiderivative just ends up being the constant times natural log of the absolute value of the denominator. Same thing here, except that it's with a y plus 2. And so we end up with this solution. And like I said before, we're taking all the integration constants and combining them together on the right-hand side. I'm going to label that constant 1. This is called an implicit solution because we haven't solved yet for the y. If we want to solve explicitly, we have to do some pre-algebra stuff, or pre-calculus stuff, some algebra manipulation. We could use, we could multiply everything by 4 here. so that that would get 4x plus some new constant on the right-hand side. We could undo the log with e to the right-hand side equals e to the left-hand side, so they would cancel on this side. Then you'd have that fraction equals, because of the absolute value sign, it would be plus or minus this value on the right-hand side. But when you have 4x plus c to the 2, c2 in the exponent, that's two separate things. So this just becomes a new constant, which now I'm going to call c. And then that means that if you kind of multiply both sides here, you'd get y minus 2 is plus or minus this constant times e to the 4x times y plus 2. And if you carefully multiply this out and gather all the terms on the right-hand side, or on the y's on the left-hand side, you'll get that because there's a plus or minus here, you have y equals 2 1 plus c over e, or times e to the 4x over 1 minus c e to the 4x, or these two signs are reversed, right? But because the constant could be positive or negative, you can just represent that as one is positive and one is negative. So this is a representation for all the solutions that where this has been solved for y. Okay, so this is how you would handle an absolute value if you needed to. Treat it as a plus or minus and then see what happens. You might end up with two forms of solutions, or maybe they can be combined into one when you consider the constants are both positive or negative. All right. So here was the original differential equation. dy dx is y squared minus 4. We went through the solution steps to separate the variables. We did partial fraction expansion. Oh, there's one more thing I wanted to mention. So if you have this partial fraction expansion, this can be a big pain, especially if this goes above degree 2. So if you want to, especially on practice, there are many online calculators that do this. So let me show you one of them. If you go to my website, mrfelling.com, and you go to the Math Applets and Resources section, for Calc 3 differential equations, there's a link here to a partial fraction expansion calculator online. And then you can go there and enter something like that was in the 1 over y squared minus 4. So if you were to just say, leave this saying partial fractions, and then type the fraction symbol here that they gave, and put 1 over it. Now you have to use x in their case. So I'm going to use x squared. Wait a second. Was it, what was the value again? It was 1 over y squared minus 4. So I'm just going to put x and then squared minus 4. And then if you say go, it will go ahead and expand that for us. See how that wrote that the x plus 2 term, 1 over x plus 2, the constant is negative 1/4, and the x minus 2, 1, the constant is positive 1/4. So that's another way to get this very quickly. So this is a pre-algebra topic or early calculus topic, so we don't need to spend a lot of time on that. You're welcome to use these partial fraction calculators whenever it makes sense to do that. Okay. All right, so now that we have this solution that's in this form, if we wanted to, we could take the derivative of this using the quotient rule and verify that this is a solution, but it is indeed a solution. We know that there's a whole family of function curves depending on where we set c, right? So if we happen to have an initial condition, we would get a different solution curve. Like, for example, if we were given the condition y at x equals 0 is negative 4, then if you plug in 0 for x, you get 1 plus c over 1 minus c times 2 has to equal negative 4. And when you solve for c, you get 3. So that would be a 3 here and here. On the other hand, and that would produce this blue curve if you graph it in a calculator. On the other hand, if you were told that y at x equals 2 is negative 2.2, then when you plug in 0 for the x here and here, you'd get c plus 1, or 1 plus c over 1 minus c times 2 has to equal negative 2.2. When you solve for that, you end up getting that the constant of integration is 21. And when you fill that in, you get a little bit different curve, right? So we know that there'll be a different curve depending on what the initial conditions are. This represents a family of curves or a general solution until we establish the constant with particular initial condition. Okay. One thing that the book points out, I don't think this is hugely important. I don't remember it popping up frequently as we move throughout the rest of the course, but you can lose a solution using this separation of variables method. And that's because when you separate the variables, we're typically dividing both sides of the equation by something with y on this side. Not always, But like in this case over here, where we divided both sides by that, that means that although this equation is algebraically equivalent to that, it doesn't necessarily have the same domain, right? Because over here, any y value is okay in the original differential equation. But with our separation here, we have actually got a place here where, since this can be factored into y is 1 plus 2 over 1 minus 2, there are two values, y equals 2 and y equals negative 2, where our transformed equation actually is undefined, right? So our solution will not capture those particular cases. So if there are any places where after you've rearranged your equation, you have a case where you could divide by 0 or anything else that would cause something to be undefined, you should actually manually check any values, right? That means checking the two solutions. So for example, if y was 2 in the original equation, that would make this, let's see, complete family selections. Yeah, let's just check those. So in other words, what we're saying is when we come up with this solution, this technically has as long as y is not equal to 2 and y is not equal to negative 2 attached to it. That's kind of hidden in the background. So just to make sure that those two things are not also solutions, we should say, well, what if the solution was y equals 2? And let's plug it in the original differential equation to see. If y was 2, then the derivative of y with respect to x would be 0. And if you plug that in over here, you would get 0 equals 2 squared minus 4, which is 0, which is indeed a solution. So that means that this is also a solution, besides the complicated solution we found. And if you did negative 2, the derivative would be 0. That also makes the original equation true. So we had two extra solutions that weren't captured here that are also part of the solution set. Okay, actually this one, y equals 2, is included, because if we set the constant c to 0, it would be 2 times 1 over 1. And this one is actually built into here, but this one is missing, right? So we would have to include this one. Now, that's a real esoteric thing. Honestly, I don't remember that we have that situation come up frequently, but I think especially since you may use this in science classes or whatever, we have a possibility that we have a dropped solution once we start manipulating the equation by dividing by things. Okay. All right, let's try another one here. You can pause this video and try it, and then I'll work this out. And then once you have the implicit solution, try to find an explicit solution. While we're doing that, it says, let's assume that y is always positive. There must be some issue with that. So we'll go give this a try. So pause this and then try it. Okay, so here's my solution for this. It looks like I can separate this. K is understood to be a numerical constant, so I could write this as 1 over y dy equals k dx. And then my solution method then would be to take the antiderivative of both sides. This is a y, not a 4. Okay, so the antiderivative here is natural log of the absolute value of y. And over here, it's kx plus an integration constant, which is really the sum of both integration constants for both sides combined on the right. Okay, this is the implicit solution right here. Right, it shows the relationship between x and y. And if you were to do implicit differentiation here and solve for dy dx and plug it in here, it would act equal ky. Okay. Now, if we want to do an explicit solution, I'm going to have to I'm going to solve this for y. So the way I would do that is to go e to this side equals e to this side. So these would cancel, and I'd be left with the absolute value of y equals e to the kx plus c, which is the same as e to the kx times e to the c, which is just another constant. So it's a constant times e to the kc. Maybe this is a different constant than that final one. Okay. And so since it said you can assume y is always positive, we could just write this as y equals some constant times e to the kx. This is the explicit solution because it's explicitly solved for the y variable. Okay, does that look familiar? It should, because this is a equals p e to the rt. Right? This is the solution for, say, compound interest. And when we get to the modeling section, we're going to talk about why this is true. This particular form of differential equation shows up whenever you have the rate of change of something is proportional to the current value. So if you have a little bit of money in an account, then you get a little bit of change in the money. in terms of interest. But if you have a lot of money in your account, you get a big change in the amount of interest, a change in the value, right? So that's why compound interest, for example, compounded continuously, it's really the solution to this differential equation. And in our modeling unit right before spring break, we'll talk more about modeling and using these for real situations. Right now, we're just kind of dealing with the solution methods. How do you solve them? Okay, let's do another one. This one's an initial value problem. So we'll start by trying to separate these right here. It looks like we have y as the dependent variable and t as the independent variable. So I'm going to move the t over here. What I would do is first multiply everything by t. So dy equals, oh wait, dy plus 2y dt equals dt. And then I would get the t terms on the other side. So that means dy equals negative 2y plus 1 times dt, right? And then that means we could divide both sides by this term. So we would have 1 over, let me write that as 1 minus 2y dy equals dt. And now I've succeeded in getting the y's on this side and the t's on this side. So I like to multiply it to get rid of any fractions first. So I'd multiply everything by dt. Then I'd move all the terms of the dt over there, factor out that dt, and then that gives me something to divide out. Okay, now to solve, we'll take the antiderivative of both sides. Okay, I think we can do a u sub on this side. Let's do that. U is 1 minus 2y, which means du dy is negative 2, which means du is negative 2 dy, which means dy is negative 1/2 du. Now I'm going to substitute this. This is going to end up being 1 over y, and the dy is negative 1/2 du equals just the integral over here of dt. So this is going to be negative 1/2 natural log of the absolute value of u. And this one's just going to be equal to t plus some integration constant. Let me resubstitute the u again. So I'll end up getting negative 1/2 natural log of what u was, which was 1 minus 2y, equals t plus an integration constant. There's the explicit solution. Okay, if I wanted to find an implicit solution, I need to solve for this. So what I would probably do here is multiply everything by negative 2 to get natural log of 1 minus 2y equals negative 2t plus some new constant. This is just negative 2c. Let's call that c1 so that we can just rename this one c. In fact, I'll call this c2. So I'm going to write this as negative 2t plus 2c2, natural log of 1 minus 2y. Okay, to get rid of the log, I'll go e to both sides, which means on this side, I've got absolute value of 1 minus 2y equals e to the negative 2t plus c2, but that's the same as times e to the c2, which itself is a new constant, so I'm just going to now call that c, e to the negative 2t. Okay. All right, and then let's see. I believe I can drop this absolute value because of the c, right? The only thing that happens here is that this 1 minus 2y is just equal to plus or minus c e to the negative 2t. But since c, we haven't established what sign it is, we can just absorb that into the c. So it's just 1 minus 2y equals c, some constant, could be plus or minus. So there's the, and we're almost done here. We've got negative 2y equals c e to the negative 2t minus 1, and then divide everything by negative 1/2. So it's going to be plus 1/2. Okay. These are both over 2. So maybe I could write it this way as 1 minus c negative 2t over 2. All right, so there's my explicit. So it's still a family of solutions because I haven't established the c. But now that I have an initial condition here that y at x, when x is 0, y is 5/2, I can now establish what that is. Let me do that up here. Okay, so I'm just going to plug into this equation this statement. Y is 5/2, and then I'm going to put 0 in for the x. E to the 0 is 1, so this is like saying 1 minus c over 2 has to equal 5 over 2. So when you multiply both sides by 5, you get 5 equals 1 minus c, and therefore c equals 1 minus 5, or negative 4. Right? So our final solution would be y equals 1 minus negative 4, so plus 4, e to the negative 2t over 2. That's my final particular solution there. Write it better down here. Y equals 1 plus 4 e to the minus 2t over 2. If you were to graph that, that's the specific function curve that fits this differential equation where the slopes all match up, but it also goes to the point x is 0, y is 5/2. All right. Okay, and then I've got one more example here. This is one of the homework problems, but give it a try. And if you get stumped, we can look at this because there's a lot of kind of tricky stuff going on. Let me get this started for us. Okay, solve and find an explicit solution for this given the initial conditions. So we'll start with this. We've already got the y's and x's separated, so let's get them on separate sides. It doesn't really matter which one now. In this one, we haven't really established what the independent and dependent variable is yet. Okay, well, let's do this. Let's move one of them to the other side. So we've got square root of 1 minus y squared dx equals square root of 1 minus x squared dy. And then let's divide each side by the other one's square root. So we end up with 1 over the square root of 1 minus x squared dx equals 1 over the square root of 1 minus y squared dy, which means now we would integrate both sides to find the solution. And it turns out that if you look up in an integral table, 1 over the square root of 1 minus x squared is a little too complicated to do with just straight u substitution or anything else like that. You could use, I guess, trigonometric substitution, but at this point, I just go ahead and look up in an integral table. It turns out that this is the form for the inverse sine. The integral of this is the inverse sine of x. And over here, it's the inverse sine of y plus some integration constant. Okay. So that's an implicit solution. Okay, and while we're at it, let's go ahead and plug in the initial condition right now to establish what the constant is. Okay, so when x is 0, y is this. So if I plug in 0 for x, I have to get y is the square root of 3 over 2. All right, so what this is saying is the inverse sine gives an angle whose whose y value is 0 on a unit circle. So let me draw a little unit circle here. We're looking for places where y is 0. So where is y 0? Y is 0 here and here, but the inverse sine has a range here. It always produces values between negative pi over 2 and pi. And so this answer over here would be 0. Okay, let's do the same thing for the inverse sine over here. If we draw a unit circle, we're looking for places where the sine is the square root of 3 over 2, which is the larger of the special values. So we have to have places like this, right? Square root of 3 over 2 could be here or here. So it looks like the two angles are either here or here. But again, the inverse sine has a range out here. So this is going to be pi over 3, not 2 pi over 3. So it looks like this is going to end up being pi over 3. So what this is saying is 0 has to equal pi over 3 plus c. Therefore, c has to equal negative pi over 3. And that means our implicit particular solution would be inverse sine of x equals inverse sine of y minus pi over 3. Okay, so there's the implicit solution. Okay, and then could we solve this for y to get an explicit solution? I think we could. We could say inverse sine of y is going to equal inverse sine of x, and then when I move this to the other side, it'll be plus pi over 3. Okay, and therefore y would have to be, you'd have to take, to undo this, you'd have to take the sine of both sides. So you would get y equals the sine of the inverse sine of, these would cancel and leave y, but the sine of the inverse sine of let's see, I'm going to get ahead of myself here. Yeah, inverse sine of x plus pi over 3. There we go. All right. So how are we going to do that? Well, if we wanted to go further, I mean, this is the solution. If I wanted to write this a little nicer and get rid of this inverse sign, maybe I could do this. I could say, yeah, this would be considered the answer, but on my notes, I wrote even further here. So I'm looking at what the book did for their answer for the homework. So if you're trying to see why the book got the answer they did, this is, I'm going to employ a trig identity here. This is sine of u plus v. And there's a trig identity that says that sine of u plus v is equal to the sine of u times the cosine of v plus the cosine of u times the sine of v. So if this is my u and this is my v, then that means this is equivalent to, using a trig identity, the sine of the u, which is inverse sine of x, times the cosine of v, which is pi over 3, plus the cosine of the inverse sine of x times the sine of pi over 3. Okay, well, the sine of the inverse sine, these cancel and leave x, so this is x. And the cosine of pi over 3, well, at pi over 3, the cosine is 1/2. And then we've got this cosine of inverse sine of x, and we've got sine of pi over 3, which is the square root of 3 over 2. So the last bit to getting this to look in some sort of nice form, because this is y equals this, would be to figure out finally, well, what is this thing? What is this cosine of inverse sine? Okay, well, what we can do is employ a trick from way back in Honors Algebra 2 or pre-calculus. We can make like a little triangle, right triangle here, and just define one of these non-right angles as theta. So what we're basically saying is this angle here is this inverse sine of x is some angle, which we can call theta. And so this is basically saying that we've got the cosine of theta, right? And we're trying to figure out what the cosine of theta is, right? But for this angle, this theta is such that that the inverse sine of x is equal to that theta. Therefore, if I took the sine of both sides, the sine of theta has to equal x. And remember that sine is opposite over hypotenuse. So if we just made the opposite side of this angle x and the hypotenuse 1, we could use the Pythagorean theorem to solve for this side, which is the square root of 1 squared minus x squared. And then we could say, all right, then the cosine of theta is just the cosine of this angle. So what is the cosine of theta? Well, the cosine of theta is going to be the adjacent over the hypotenuse, which is the square root of 1 minus x squared over 1. And that means that this whole thing here is really the square root of 1 minus x squared times square root of 3 over 2 plus 1/2 x. Okay, so finally writing this the nicest way, it would be that y equals 1/2 x plus the square root of 3 over 2 times square root of 1 minus x squared. This is the cleanest form to write the explicit solution. So if you try the homework problem and you're unable to get this, I would say, now that you've seen it, try it on your own. But if you're stumped as to how they went from that to this in the answer key, that's the further steps. A lot of fancy trig. All right, that's it for this video.